Welcome. In this session, we will look at some examples where limit in the sense we defined before does not exist, and we'll also look at some ways of extending the concept to cover some of these situations. Our first example is the greatest integer function. At x, its value is the largest integer which is less than or equal to x. If x is an integer, say 0, 0 is less than or equal to 0, 0 is an integer, so the value is just 0. It works for any integer, so value at 2 is 2. If I take 0 point something, say 0.9, 0 is less than or equal to that. The next integer, 1, is bigger than 0.9, so the greatest integer function at 0.9 is 0. But if I take 1.1, 1 is less than or equal to that, so the greatest integer function jumps to 1. It doesn't matter how close you are to 0. On the left, if you take 0 point something, 0 is less than or equal to that, but 1 is not. So we have to take the value as 0. But as soon as you cross 1, you have 1 point something, 1 is less than or equal to that, so the greatest integer function is 1. So on the left we always 0, and the right we always get 1. So the limit doesn't exist because the two sets of values are not approaching a single number. Note that if you look at only one side, everything is fine. In fact, for values of x close to 1 and to the right of 1, the function is 1, which is as close as you can get to 1. On the left, you get 0. We can so extend the concept of a limit by using what are called one-sided limits. One-sided limits are like two-sided limits, but we look at only one side. The notation used takes a bit of getting used to. We will write when you look only on the right hand side of the number as the limit as x approaches c with plus as a superscript. The way you can remember this is that we allow x to be a number of the form c plus a small positive number, and we make that small number smaller and smaller. So for the greatest integer function, the limit from the right is 1, because if you look only on the right hand side, values are all 1. But the value limit from the left is 0, because if you look at values on the left, you get 0. The usual kind of limit, the one we defined before, is called a two-sided limit when we want to specifically refer to that. Of course, if the two one-sided limits are equal, that means the two sides are approaching the same number, so it's a limit in the old sense. And if the two-sided limit exists, it must also work for each side separately. So each one-sided limit will be the two-sided limit. So this leads us to the conclusion that the two-sided limit exists and is equal to L if and only if both one-sided limits are equal to L. Another situation where the limit doesn't exist is shown by the function 1 over x squared. If you look at the values of this as x approaches 0, when x is 1, 1 over x squared is 1. If x is 0.1, x squared is 0.01, its reciprocal is 100. Since we are squaring, the sign of x doesn't affect the value, so we get 100 on both sides. If x is plus or minus 0.01, x squared is 0.0001, reciprocal is 10,000. At 0.001, reciprocal of x squared is 1 million. So the trouble here is that these have a pattern, but it's not approaching a single number, but it's going away from every number. If you look at the graph, it looks like this. So as we make x closer and closer to 0, x squared gets smaller and smaller, so its reciprocal gets larger and larger, positive. So the graph shoots up on both sides. So it's like the graph is approaching something, but that something is not a number. So we place an ideal point, infinity, at the top end, and say the function is approaching infinity, or we write the limit equals infinity. This is a bit different because we cannot talk about numbers getting closer to infinity. Infinity is always infinitely away. But in a metaphorical sense, 1 over x squared is getting closer and closer to infinity as x gets closer and closer to 0. We can also have one-sided limits which are infinite. And same way we can talk about limit being negative infinity. If the values are negative but the absolute value is getting larger and larger. You can have a combination which happens with 1 over x. With 1 over x, on the right, the values are positive, and the graph shoots up. On the left, the values are negative, and the graph shoots down. So we say the limit from the right is infinity, the limit from the left is negative infinity. Another reason why limit may not exist is that the function oscillates infinitely often. It's not possible to write down a function like that using only algebraic, exponential, and logarithmic functions. But we can use piecewise defined functions to do something like this. Just have a graph that goes up and down more and more quickly as you approach 0. It's not behaving in a nice way. It's getting closer to every single number between -1 and 1. So we cannot really talk about the function approaching a single number. And we draw the line here. We don't talk about limits of things like this. So these are the three situations where limit in the original sense does not exist. You have a break in the graph. So from the left and right, you have specific limits, but they are different. Or the graph shoots up or down, so you get infinite limit, or the function oscillates back and forth, in which case we simply don't extend the concept of a limit. So I will stop here and we'll talk about calculating these types of limits later. Bye for now.